Alright, welcome to the first video in heat transfer. This starts off chapter 1, which is an introduction to heat transfer. One thing that I want to get started off with is the difference between thermodynamics and heat transfer. Thermodynamics, if you recall from your course, if you have already taken it, is that you're looking at how you get work out of a system. How do you analyze how much work you get out, how you analyze its efficiency of a system, and stuff like that. Now, for thermodynamics, you have to put heat into a system in order to get work out. Now, for heat transfer, it's not like that at all. The heat that you put into a system, you want to analyze how it goes, how does it travel, and that's just, and more specifically, it's not just a system. It can, the system that you're looking at doesn't have to be a system that outputs work, or you have. You're not looking at a system that outputs work. Versus for thermodynamics, you are looking for work of a system. In heat transfer, you're just looking at a system that doesn't necessarily have to output work, and you're looking how heat travels throughout that system. And I hope that explanation makes sense. It might be a little bit over-explained in my. It might be a bit over-explained, but I hope it helps with the distinction. Now, to start off, we're going to look at the first mode of heat transfer, and that's conduction. What is conduction? Now, conduction, you probably saw the governing equation in your physics course, in one of your physics courses, or maybe you didn't. For me, the physics course that I took, it did go over Fourier's law. All right, start off. What is conduction? It is energy diffusion due to molecular motion. And what is that saying? It is saying that particles randomly move and they're going to transfer energy. Excited particles are going to go transfer energy to less excited particles, right? When you look at a solid, when you look at a microscopic level, right, consider this particle. It's bigger for a reason. It has a lot of energy. And consider this small particle. It's smaller because it has less energy. Now, somewhere in a solid, these particles are going to interact. They're going to hit each other, and that's what energy transfers. And that's what's going on in the conduction, and it specifically occurs in a solid. It can occur in a static fluid, but it really dominates in a solid as opposed to a static fluid. As opposed to a fluid, sorry. Now, the governing equation, as I mentioned earlier, is Fourier's law. Fourier's law states that the heat flux is the thermal conductivity of a solid or a fluid times its temperature gradient with a negative sign. Why is that negative sign there? Now, that's important. Now, you probably remember from the physics course, again, if you probably remember the Fourier's law from your physics course, and sorry, I'm butchering my words, is that sometimes you can make the approximation is that this is equal to delta t over delta x. So you can write it as t2 minus t1, x2 minus x1, or honestly, it should be the length of the wall or whatever. We're looking at a wall here. Now, this is for a wall. This is for a wall. Now, I will explain this more later on once we start the conduction chapters. But for this case, we're going to do for a wall, and you're going to assume that the temperature gradient is linear, because that's when this equation holds true. All right, now I want you to consider two cases, because this is where I explain the negative sign. So you have this wall, you have T1, and you have T2. Consider T2 is greater than T1, and then T2 is less than T1. We're going to consider both cases. Now, with the negative sign, when you do T2 minus T1, without the negative sign, right, this is going to be greater than 0, and this is going to lead that your heat flux is moving to the right. But that's wrong. Because since T2 is greater than T1, heat has to flow that way. And that's for this case. Right? That's why that negative sign is there. Because without that negative sign, it's going to say that the heat flux is moving to the right, where it's wrong. From the definition of conduction, we know that heat has to go from hot to cold, and I wrote it up here. That is what this bullet point is saying, that a harder particle is going to transfer energy to a colder particle. Now consider T2 is less than T1. In that case, when you do T2 minus T1, you're going to get something that's less than 0, meaning that your heat flux is moving to the left. But that's wrong. In that case, the heat flux has to go to T2, and that is this case. That is why the negative sign is there, and I hope that clarifies some confusion that some people might have about the negative sign and why it's there. But yeah. Alright, next is I'm going to touch lightly on thermal conductivity, just to explain what it is. Now, in simple words, it measures how fast a material transfers energy. And that's basically what it is, and it varies a lot in materials, but I'll explain that later. And that's basically conduction. Now I'm going to do a small, quick example. It's example 1.1 from the textbook. And, sorry, I need to pull up the example, because I'm not going to do the calculations. I'll do the steps, but not the calculations. I'll get the numbers from the textbook. Okay. Now I summarize the word. I summarized the problem here. And now, depending on your professor, they might have you do like an outline for your solution problems. That's what I'm doing. You don't necessarily have to do it. It's how I was shown. But yeah. So first off is start with your known. We know that a wall has inner and outer temperatures at 1400, I think 1400 Kelvin and 1150 Kelvin respectively. We know that it's 0.15 meters thick, 0.5 meters tall, 1.2 meters wide, and it has a thermal conductivity. You want to find the rate of heat loss. Now you're going to assume some stuff, and some of these assumptions, they might not make sense, but we will go over them once we start the conduction chapter. Alright, so we're going to assume steady state, meaning heat does not vary with time. That's what this assumption is saying. It's 1D conduction. Again, you might not know what that means, but I will explain it later in the conduction chapter. And it's has constant thermal conductivity. Now, in the textbook, you're given the schematic for the problem. Sometimes you're not, but in case the problem doesn't give a schematic, you might have to draw something out to help you visualize the problem. So in this case, I'm just going to redraw what the textbook has. So we know T2, we're going to say that's the outer, right? So that is 1150 Kelvin. T1 is 1400 Kelvin. Now in this case, the heat flux is going to be moving to the right. That's what that's saying. And then you have that it's 0.5 meters tall, 1.2 meters wide, and 1.5 meters thick. Now, next we're going to start with the analysis. This is one thing I want to point out is that this problem is something that you see in your physics course, but what you're going to learn in heat transfer is you're going to basically learn how to find this temperature gradient and how to, basically is what it is, because you won't always look at a plain wall, right? You're going to look at something way more complicated than a plain wall. Okay, so from the Fourier's law, we know that for a plain wall, it's going to be T2 minus T1 over its length. Now the length, one thing I want to clarify is that heat flux will always be perpendicular to the area that is traveling. As you can see, the heat transfer is occurring across this area, so the heat flux is perpendicular to that. Okay, that's why in that case L would be the thickness, or I'm just gonna write T for thickness, because sometimes people can get confused on. I know I can. people get confused on just variables and how I name it. The thickness, right? So in that case, the heat flux is 283 watts per meter squared. And then from there, you need to multiply by the area. The area of the heat flux, which is this blue shaded region that I outlined. So that area is going to be, the area for the heat flux is 1.2 times 0.5. And when you evaluate that, the heat loss is going to be 1,700 watts. As a simple example, it just shows how to work with Fourier's law. But yeah, I hope you guys enjoyed this introduction to conduction. For this one, I did the example within the video just because it's a very straightforward example. It's something you probably saw in the physics course. But yeah, next up is convection.